All right, so we are going to look at section 4, which is initial conditions and particular solutions. So this isn't really any new math. This is just kind of getting into some of the things that we might use this integration for. So we have seen that when you take the antiderivative, when you apply the integral, we get a plus c. That's our constant of integration, okay? Now, with any function, remember that if we have f of x plus c based on our function transformation rules, all that does is shift the function up or down. So that's what that constant of integration does. When we are finding an antiderivative, we're not just finding the antiderivative because there's infinitely many. We're finding an entire family of functions. Okay, so for example, if we look at y equals the antiderivative of 3x squared minus 1 dx, that integral comes out to x cubed minus x plus c. So that graph x cubed minus x is going to be a cubic function. Any of those values of c, that's what this picture is showing us over here. If c is equal to 1, then that's this graph that's in bold. But if I change the value of c, all that does, it keeps all the shape of the graph the same, but it moves the graph up or down, okay? So in many of the applications of integration that we're going to look at the rest of this unit and into the next, you are often given enough information to determine a particular solution. And so that helps us determine what should the value of C be based on the what we would call initial condition that we have been provided. Okay, so for example, in the graph shown, only one curve passes through the point 2, 4. And so if we want to figure out which one that is, then what I know is that when x is 2, y is going to be 4, or f of x is going to be 4. That's our y value. So we can go ahead and plug those values in. We get 4 is equal to 2 cubed minus 2 plus c. So 4 is equal to 8 minus 2, which is 6, plus c. So that tells us that c is going to be negative 2. So the particular solution that we have just found, the general solution is what we get in terms of c. So general solution still has the plus c on it. The particular solution is when we solve for c. And so now we know that the particular solution we have found is x cubed minus x minus 2, and that's the one that's in bold, or sorry, no, it's not. It's this one right here, passes through negative 3 to negative 4, somewhere is the point over there that we are looking for. That is what we are finding. Okay, so that's all we have to do on any of these is we're going to take the antiderivative just like normal, and then we're just going to use the initial condition that we have been given. So I think we've only got, 3 examples. This is a short section, so we'll be done here pretty quick. So number 1 says, find the general solution of f prime of x is equal to 1 over x squared for x greater than 0, and find the particular solution that satisfies the initial condition f of 1 is equal to 0. So if f prime of x is equal to 1 over x squared, we're saying that's the derivative of our function. If f prime of x is equal to 1 over x squared, then that means that f of x is going to be equal to the antiderivative of 1 over x squared dx. And remember, in order to use the power rule, we need to rewrite that using our negative exponents. So the rule f of x is add 1 to the exponent. That makes it x to the negative 1. Divide by the new exponent, which was negative 1, plus c. So we get for our general solution, negative 1 over x plus c. Now, we need to determine the particular solution using the initial condition that we have been given. F of 1 is equal to 0. So when x is 1, f of x is 0. So we're going to plug that in using the fact that f of 1 is equal to 0. That tells us that 0 is equal to negative 1 over 1 plus c. Well, negative 1 over 1 is just negative 1. So we add 1 to both sides, and that tells us that c is equal to 1. So our particular solution is f of x is equal to negative 1 over x plus 1. So we've moved from the general solution, which represents a whole family of vertical shifts of the same function, to finding the one specific function that goes through the ordered pair 1, 0 that we were given. Anybody have any questions on that? Okay, will you go ahead and take a moment to try number 2? So we want to find the general solution of dy dx. Again, that's the derivative, so you're going to integrate on the other side. And find the particular solution that satisfies the initial, oh, that's spelled wrong, initial, the initial condition that y is equal to 7 when x is equal to 0. See if you can try that yourself. All right, so let's start with our integral. So remember, you can go term by term. So the antiderivative of 5 secant squared x, remember the constant just carries on through. This is going to be, oops, my pen's asleep, wake up. This is going to be 5 tangent of x minus the 3/2 is a multiplier, so we carry that down. We need to add 1 to x to the 1/2, so that makes it x to the 3/2, divide by 3/2, which is times 2/3 plus c. And boy, that works out nicely. The 2/3 and the 3/2 cancel out there. And so now we have for our general solution, y is equal to 5 tangent of x minus x to the 3/2 plus c. Okay, did I start the recording again? Yes, I did. Okay, does anybody have any questions on that antiderivative? Remember, that's called our general solution because we still have that constant of integration that can be anything. So now we need to use the initial condition when x is 0, y is 7. So we're going to plug in those values. So let's use that here. X equals 0, y equals 7. So 7 is equal to 5 times the tangent of 0 minus 0 to the 3/2 plus c. Well, that's just 0. Tangent of 0, let's see, is sine over cosine. That is 0 over 1. So this is also 0. So that tells us that c is 7. So now we're ready to give our final answer, which is the particular solution that has 7 instead of c. So the final answer is y is equal to 5 tangent of x minus x to the 3/2 plus 7. That is our particular solution here. Anybody have any questions on this one? So we're going to be revisiting our motion problems, velocity, position, acceleration, all of those sorts of things throughout the course of this integration unit, because if we can say the derivative of position is velocity, then that would mean the antiderivative of velocity is position. So we can work both ways through that. So this will be coming back. And so this is kind of a introduction to that here using these initial conditions. So it says a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function given the height s as a function of the time t. Okay, so velocity here is going to be 64 feet per second. That's what we know about the velocity. So we can start, if you remember at the beginning of the year, we learned that position function for a free falling object, whatever. This is kind of where that function comes from. So we start by knowing that our initial velocity is 64 feet per second. So we are going to take, we know that V of t is 64 feet per second. Now, here's where we kind of have to start from. We only know the initial velocity. We don't know the velocity function. So we can't really start there. I shouldn't have written that down just quite yet. What we do know for sure is acceleration due to gravity. So that's actually where we need to start. Acceleration due to gravity on Earth is always the same. Now, you physics people are probably thinking negative 9.8. That is meters per second. We have to know our acceleration due to gravity in feet per second, because that's typically in this class, you're going to see feet. So acceleration, we saw this before, I think, but you may not remember. Acceleration due to gravity on Earth in feet per second is negative 32 feet per second. In meters, it's negative 9.8 meters per second. That is going to be something that you're expected to know. That information will not always be given to you. So if that's not common knowledge to you, put it on flashcard, add that to your things that you want to study. And the acceleration due to gravity is always the same. It's constant on Earth. So that's the function that we can start with. What's interesting about this problem is we have to work from acceleration to velocity, and then from velocity to acceleration, which is why we've been given two initial conditions. We're going to have to use them both. So this one's going to be a few different steps. So we are going to start with the fact that A of t is equal to negative 32. That, again, is just knowledge you're expected to know. So that's where we can start. So now, if I want to get to V of t, that's going to be the antiderivative of negative 32 dt. Why dt? Because t is the variable we're using with respect to time. So that's why our variables are going to be all in terms of t. So that's an easy integral. We get negative 32t plus c. That's our general velocity equation. We need to know the specific velocity equation for this particular moment. And so they tell us the initial velocity is 64 feet. Initial tells us that's when t is 0, 64 feet per second, sorry. So we know that v of 0 is equal to 64. So we can go ahead and put that in. 64 is v of t is equal to negative 32 times 0 plus c. Well, that's just 0. So it turns out that c is just going to be 64. So now what do we have? We have our general or our particular velocity equation for this scenario. V of t is equal to negative 32t plus 64. Any questions on that? Now, to get from velocity to position, we are ready to integrate that. So S of t is going to be the antiderivative of negative 32t squared plus 64 dt. You should see pieces of that position of a free falling object equation that kind of come out here. Whoops, I got ahead of myself. That's just a t, not a t squared. It's going to be a squared when we're done integrating. Okay, so take our antiderivative. That tells us that S of t is equal to, this is going to be negative 16t squared, because you have to make it a squared and then divide by 2, plus 64t plus c. Now we can use our initial position, which was given, which tells us that S of 0 equals 80. So we plug in, nope, yep, 80, and we plug in 0. That's going to be 0 plus 0 plus C. So that tells us also that C is 80. So our position function, which is what we were trying to find, is going to be S of t is equal to negative 16t squared plus 64t plus 80. And that is our final answer. Okay. So the last question, when does the ball hit the ground? This is not a calculus question. This is like an algebra 2 question. So we're just going to set that equal to 0. So we have 0 equals negative 16t squared plus 64t plus 80. I know you can factor out negative 16 here. We may not need a calculator. T squared minus 4t minus 5. Nope, this is factorable. So we get t minus 5 and t plus 1. So when does the ball hit the ground? At t equals 5 or t equals negative 1, but negative 1 doesn't make sense. So 5 seconds is when the ball hits the ground. If this was a calculator question, you could just find the zeros that way. But if it was a no calculator question, you would know that it was likely going to be factorable because that they wouldn't give you an ugly one if it was no calculator. All righty.